Welcome to our first AP Chemistry lab, the formula of a hydrate lab. I think the name is a little bit of a misnomer. We are not finding the formula of the entire hydrate. What we're trying to determine is how much water is in the hydrate. I want to introduce you to a very common hydrate. Okay. So this is calcium chloride. This is damp rid. What is the purpose of damp rid? To absorb moisture out of the air. Right now this is the anhydrous form. There's no, or if any, just a little bit of water with these crystals. But if I were to open up the stopper and let it sit here, these crystals would grab water from the air and form new crystals. It will grab moisture out of the air and form a crystal that locks that water inside the crystal. So of course, to keep this anhydrous, we need to keep it tightly covered. What we're trying to do in this lab is determine what's the ratio between the calcium chloride salt and the water molecules that would be in that hydrated crystal form. So a hydrate is a salt that has some water trapped inside the crystal as it forms the crystal. We don't include water in with the formula for the salt itself. We put a little dot in between, and I know this, it looks like the multiplication sign from math class, but it's that little black dot between the salt formula and the water formula that tells you that together is a hydrate. It would be very easy to find the ratio if we could find the mass of the salt that we're using, convert that to moles using the molar mass, add the perfect amount of water to the crystal, find the new mass, do some subtraction to find how much water we added, and then use the molar mass from the periodic table to find that as well. However, in that statement I just said, the word perfect in there is not going to work. There is no way to know the perfect ratio with just empirical data. You can't just sit here with the salt and go drop by drop till you see a perfect ratio occur, because you'll never see it. So we have a little trick we're going to use. We're not going to use calcium chloride. We're going to use copper 2 sulfate. Copper 2 sulfate hydrate. This is already hydrated. There's already water locked in these crystals. This has water locked in it. So you're probably thinking, well, how do we find how much water is in there if the water is already there, if we can't measure the new mass while adding it? We're going to be clever. We're going to measure the mass after getting rid of the water. So we're actually taking a hydrate and we're going to dehydrate it to find how much water was lost in the process. And then we can calculate backwards, just simple stoichiometry, and find a ratio between the copper 2 sulfate and the amount of water. And I'm not going to tell you what that ratio is. That's your goal of the lab. Okay, so that's what we're doing in the lab. Again, we're finding the form of the hydrate. Specifically, we want to know what the ratio of salt to water molecules are in this hydrate, because a hydrate is a salt with water. All right, so I want to introduce you to the setup, the equipment we will be using in the lab. Okay. We're going to be using crucibles. There is a reason that the book is called The Crucible. If you want to discuss why after we're done with this lab, that'd be fine. It has nothing to do with this lab though. But this is a crucible. It's made out of porcelain, this particular one. They're made out of all sorts of things. This is actually a Coors crucible by the same company that it sounds like, Coors. There's also a neat story behind that. We could talk about that after the lab. But we're going to use this crucible, and to get it into our ring stand and ring, we're going to use a clay triangle. So clay triangle just lays over the ring, and we set the crucible in. Now the first step in this lab is going to be purifying the crucible. If we don't have a pure crucible, If there is still leftover chemical garbagey whatever from last year in that crucible, we're not going to be able to accurately get the mass of the hydrate and accurately find the mass once it has been dehydrated. So we will take a day to purify our crucibles. This is a very common step, and if you were asked on the AP exam to outline the steps for finding the mass of a hydrate or something like that, anything involving the crucible, you would certainly need to state that you're going to get the crucible to constant mass. That is our term for saying that it has been purified. So why do we get it to constant mass? Well, we don't want the mass of the crucible to change during our experiment. That would influence the results in a bad way. We would not get accurate results. How do we get the crucible to constant mass? Well, the good news is it's a simple cycle. We're going to heat the crucible, we're going to let it cool, we're going to find the mass. And then we'll heat the crucible, and we'll let it cool, and we'll find the mass. And we'll heat the crucible, and we'll let it cool, and we'll find the mass. And we repeat this cycle until the crucible is purified. So hopefully you're asking yourself, well, how do I know when the crucible is purified, when I can stop this cycle? We call it getting the crucible to constant mass for a reason. Say, for instance, I heated and cooled and massed the crucible 6 times. And here's the results from that. You can see my first time of heating, cooling, and massing, I got a little over 48 grams. And I repeated the cycle and got about 46. And I repeated the cycle and got 45. Notice what's happening for cycles 4, 5, and 6. My mass is changing ever so slightly. Okay, this is tenths, hundredths, thousandths, this is to the 10,000ths of a gram. And I'm getting very, very, very similar results. All these numbers match except for that final number, and those final numbers are very close to each other. What's this tell me? This tells me my crucible is at constant mass. This tells me the crucible is purified. So that's what we do. We continue the cycle of heating, cooling, and massing until our data shows that it's at constant mass. It's really good to get 3 times matching. A lot of places will be okay if you get just 2 matching. But I prefer to be sure and take that one extra step and be sure that the 3rd time is matching. Do these numbers match exactly? No, but again, that change is in the 10,000ths of a gram place. All right? We're talking, what percentage of a change is that to the amount of mass? We're not even talking, the 1%. We're talking like maybe to the, the hundredths of a percent change. That is certainly close enough. These 2 numbers, not close enough. These numbers, definitely close enough. So that is the cycle. As this is the first lab in AP Chemistry that we're doing, and it's the first one involving the burners, I do want to remind you how to light the Bunsen burner. Okay. I do have the hose attached to the gas jet on the benchtop, and I have checked the hose for cracks and scars and anything else that might cause it to leak by running my fingers over it. And if there's any rough spots, that's where I look to see is there actually a hole there or not. If you're unsure, please ask. Once I know the hose is good, I'm going to be sure the valve is turned open. Again, looking upside down, right is tight, left is loose. How open or closed do you make it? Somewhere in the middle. You have time to adjust it later. Also, we're going to have the windows closed. A lot of students forget to check if they're closed, somehow assuming the people who used it last time put it away correctly, and you know that's not a safe assumption. So we're going to be sure those windows are closed. So I'm going to move this to the side for a moment. I have my valve down here open. I have the windows closed. I'm going to turn the gas on, and I can hear that the gas is running. If I could not hear the gas is running, I would put it to my ear to listen. If I still could not hear the gas is running, I would need to open this valve more. If the gas seems like it's running too much, then of course you can close the valve. That's a choice as well. You do need gas coming out of it though in order to do the lap. Okay? And again, it was lefty-loosey, righty-tighty from underneath. When you're looking from above, that means it's reversed. So I'm now closing it by turning to the left. I know it's confusing, you'll get used to it. Valve open, I can hear gas coming out. Windows are closed, I'm ready to use the striker. Again, being right-handed, I'm going to push with my left hand on the back of the striker, get it over the gas area and squeeze. And hopefully, if you've set it up right, it only takes 1 or 2 tries to get it to light. And of course, you move your hand quickly. All right. Again, do not be scared of the fire. Okay. As long as you don't just shove your hand in and start counting Mississippis, you'll be just fine. If you're really worried about the heat, get your left hand wet, and then the water absorbs the heat and not even your skin. We are not going to be able to purify anything with a flame that looks like this. In fact, this flame is dirty. If you were to put your crucible over this, it would get black soot on the bottom. Do not do this, but I do want to demonstrate. Okay, see how it's starting to put black soot on the bottom of the crucible there? That's going to do the opposite of purification. So, we want this a big blue flame. I'm going to start by opening the windows to make it blue. Okay, now I have what I would term a small blue flame. I have that inner cone there, outer cone up here. Above the inner cone is the hottest part of the flame. But again, this is a rather small blue flame. We want to purify that crucible. We're literally burning the crap out of it. Don't put that on the AP test, but that is our goal. We want to heat it up so much that any of the junk from past times of use are burnt out of it. So we're going to get a large blue flame. I call this a roaring blue flame. Can you hear the roar? Like a small jet engine, like it's ready to take off. Okay, it is ready to heat our crucible. Now by luck, I have my crucible bottom about where the top of the inner blue cone is, because that's the hottest part of the flame and that's what I want underneath my crucible. If you're not even anywhere close, that's perfectly fine. Big hint, before you move the burner underneath, raise and lower the ring and triangle and crucible to fit. Not try it underneath first and then try to adjust it. So I'm going to be able to place my flame just like that directly underneath the crucible. The bottom of the crucible is right above the inner cone. I'm hearing a roar. That's what I want. I want to heat this crucible intensely. The crucible might start getting red hot. That's just fine. It should be able to take it. I said should. What happens if it heats up too much and there was a flaw in the crucible? It will shatter, possibly shooting shards within 6 inches away and that sort of thing. That is why we always wear goggles and apron, especially when heating things. All right, so how long do we heat this? We have no way of knowing. Let's give it about 10 minutes. So pretend 10 minutes have passed. 10 minutes have passed, I'm ready for the cool cycle. Again, here's our cycle. Heat, cool, mass. Heat, cool, mass. Pretend 10 minutes have passed and it is well heated. We're going to let it cool for just a little bit right there. Okay, so a couple minutes of cooling right there have passed. Now we want to really let it cool. So we're going to move it to a desiccator. This is a desiccator. A desiccator contains a desiccant, and it's the desiccant that's going to absorb moisture from inside the desiccator. The desiccant is something similar to an anhydrous salt. It is manufactured specifically for this use so that it can last a long time, absorb a lot of moisture. We want our crucible, which is really hot, to go in here. And yes, it has been cooling here for a while and it's still really hot. Like put your back of your hand to it, you can just feel the heat emanating from it. That is really hot. I want it there. How are we going to make that transfer? Crucible tongs. Have you ever wondered why crucible tongs have that interesting shape? That is so you can literally wrap that around the crucible and gently squeezing the tongs together, pick up and carry the crucible. This really does hold the crucible very well. Now don't go doing a song and dance while you're holding it, okay? But I could easily move it. I'd want to move it like just a few inches above the tabletop if I'm moving across the tabletop. I would move it a couple inches so that if it did fall out, it's not likely to break, and I would pick it up with the tongs again. And I'm going to move it into the desiccator. And we would put the lid on, and we would let that cool. Now, why are we letting it cool in there? The whole point of what we just did was to get anything that's not crucible out of the crucible. What if while it's cooling, some of the moisture in there attaches to the crucible? Would that affect our results? Hope you said yes. So we want to avoid that. It's going to cool in the desiccator. Okay, so pretend it has cooled now. What's the next step? We've done the heating step, we've done the cooling step. Our next step is we're going to mass it. So same as you did before, because you don't want to touch it with your fingers. Even if this is cool, if we're going for purified crucible and you touch it with your fingers, you get oils from your fingers now onto the crucible, and you just completely wasted your cycle of heating and cooling. So using the tongs, you would transfer it to your balance and you would find your mass, assuming it is completely cool now. You write that down. Then you start all over again. Put it back in the clay triangle, heat it up again. When you've done that for about 10 minutes, you put it in the desiccator, let it cool completely, you find the mass. Again, how often do you do this? There is no number. There is no magic number for how often you have to do this. So how do you know when you're done? Again, when you bring the crucible to constant mass, you know it's purified and ready to go. And on the AP test, you can simply say that. First, get your crucible to constant mass. Then, because they know what that means to get your crucible to constant mass. Now, if you want to say more words than that, that's fine, but you're kind of wasting your time as well. But we get it to constant mass. All right, so that's the first step of our lab. That's a whole lot to do without actually doing the lab, I know. But the next step is faster, all right? Now that we know that is purified, we would stick some of our hydrate, copper 2 sulfate hydrate, into the crucible. How much should we use? It doesn't matter. But be sure you mass the crucible empty and the crucible with the copper 2 sulfate hydrate. That way you can subtract and you know how much you used. It doesn't have to be a particular number, usually shooting for about 1 gram works. Now you're going to heat this up and it's going to have the copper 2 sulfate in it. So just for pretend, I'm going to put a crystal of copper 2 sulfate in the crucible. Okay, got my copper 2 sulfate in there. I'm going to heat that up. Same steps as purification. I want to have the valve open. I want to have the windows closed. I'm going to light the burner. This time, however, I do still want a blue flame. I do not want to introduce soot onto the crucible, but now I want a gentle blue flame. We want to heat the hydrate slowly so it is time to release the water without burning. Okay? So it's going to heat now slowly. Still, my crucible is above the inner cone, but it's going to heat slowly, and my hydrate is going to start releasing water. And we're going to gently stir and poke this to be sure that it's being heated. Ideally, you would not put in a big chunk like I did. That was just for show. You would take small grinds of it, or even take the big chunk, put it in mortar and pestle, and grind it. All right. There is a reason we're using copper 2 sulfate hydrate. Come look inside the crucible. Obviously not a thing to do if you don't have goggles on. Look at what's happening to the blue color. It is turning white. This is why we use copper 2 sulfate for this lab. You will know you're finished dehydrating when all the blue has turned to white. If you go too far, it'll start turning brown. You don't want that. So that's why we want a small, gentle flame underneath. But you will know you're finished when this all turns white. What do you do when it's all white? Well, guess what? We're back to our cycle. We're going to heat it till it turns white. We'll let it cool in the desiccator, and then we'll find the mass. And the good news is we only have to do that once because we know we'll be finished when all the blue is gone. Now here's an extension. What if you were using a crystal that did not turn color? There's a lot of hydrates that turn color. What if you did not have a crystal though that turned color? That is a possibility. Well, just like we brought the crucible to constant mass, you would bring the crucible and hydrate, which is now anhydrous, to constant mass. You would do the cycle many, many times, gentle heating now, cooling, massing, gentle heating, cooling, massing. You would do this cycle over and over again until, again, just like before, 3 of your measurements match. And then you know you've driven off all the water that's possible to be driven off. So if you don't have a color change option to know you're finished, that's how you know you're finished. When again the crucible and hydrate get to constant mass, and you can say that on the AP test. Heat, cool, and mass the crucible with the hydrate until it has achieved constant mass. They'll know what you're talking about. That's what they want to hear from you. If you want to describe that more, that's fine, but it would be most efficient to simply say that. All right, so that is how we're doing the formula of a hydrate. Again, I want to point out, we had a purified crucible and we knew the mass of it. We added hydrate, found the mass of that. Now we can subtract and find the mass of just the hydrate. Then we dehydrated the hydrate, got the water off, and we would find the mass of the dehydrate and crucible. So now we can subtract and find the mass of the salt alone, because what's left after dehydration? Just the salt. So you really do, with those 3 measurements, knowing your purified crucible mass, your crucible and hydrate mass, and your crucible and dehydrate mass, with those 3 measurements, you can now do all the calculations necessary to determine everything you need to determine in the lab. All right, so this is the lab setup. That's how we're doing it. This is what's expected of you tomorrow. Good luck.